Today is one of my favorite topics, and so a lot of times what happens when I say that is everyone looks a little bit more scared. I hope you don't look a little bit more scared. I appreciate all the work that you guys are doing. Don't think that I don't notice. I do know how much work I give you, and I do notice when you guys are doing it, and so I want you to hear a little bit of encouragement from me along those lines and say, keep it up. We are over halfway through the quarter. I don't know if you realize that or not, but we're past the halfway point, so we're moving along and trucking along just right. All right, so we're looking today at torsion of non-circular cross sections. So you may remember all the way back to Engineering 220, whenever we looked at the stresses that were induced in torsional members, and we said at that time that what we had just derived was only good for members that had a circular cross section. And there's a lot of reasons for that, but the main kind of what it comes down to is with circular cross sections, the little elements of material undergo what is essentially a plane shear in one dimension. Okay, and that's what allowed us to use that technique and use all of that math. Whenever we go to a non-circular cross section, those assumptions no longer hold. And so what we're going to do here is look at some non-circular cross sections. And what I did here is I modeled these in SolidWorks, the simulation package. And what you see up there is that the coloring shows, where it's blue along those edges, that shows an area where there's relatively low stress. So you go out to the corners of a square or a rectangular shaped cross section, and there's a lot less stress in those corners. Where the stress is maximum is halfway through one of the flat sides, all right? And in the case of the square, it doesn't matter which flat side. It's going to be, one or the other of the two flat sides. Actually, they're going to be both at the same stress level. Whereas if you have a rectangular shape that is non-symmetric, where there's one side that's longer, you look at the flat side of the longer side, and that is where the stress values are a little bit higher. All right, and so there's, you can kind of see here that the stress doesn't really distribute the same way. One of the things that you will notice here is that inside of these members, there's kind of almost a circular shape that's inside of there. Like if you kind of look in here, there's a, sort of a part of a circular shape of stress. So, this is kind of an informal way of looking at it, but there's almost like a virtual cylinder inside of there that really takes most of the stress, and then if there's too much material outside of that, it doesn't really help you very much. Right? The further away you go, the less it helps you. So we're going to look at some analytical techniques that we can use to evaluate these type of cross sections. The other type of cross sections that we're going to look at are what are called thin-walled cross sections. And for thin-walled cross sections, they are sort of split into two categories. So let me put this on here. Here we're basically talking about rectangular solids. That's what I just mentioned here, rectangular solids. Okay, and there's a couple of equations for those. Let me just write these down, 340 and 341. That's on page 116. Okay, another possibility that we have is closed, thin-walled. Okay, which is like a tube, right? It's when you've got a closed section, but the wall is thin. And the equations that we have for that are on page 121. And those equations are 345 and 346. And then lastly, we have open thin-walled cross sections. Okay, open thin-walled cross sections are a little different than the others. This one is page 123, equation 347. They're a little bit different. The way open thin-walled members tend to work is that you can basically sort of think of it as multiple rectangular sections that are all twisting, and they essentially behave as if they are independent of one another. So if you kind of assemble a bunch of little rectangles together, it basically behaves as if each of those little rectangles is supporting torsion, but they do so relatively independently of one another. So that's what's going on there. And in case I forget to come back to it, I'm actually also going to make mention for these open thin-walled cross sections that there is an exercise problem in the textbook. It's problem 352. And it deals with open thin-walled sections where not all of the sort of segments of the section have the same thickness. Okay, there is no equation that's sort of built into the book for that case, where if you have multiple segments of your cross-section, and they each have different thickness values to them, there is nothing in the book that specifically deals with that. But this problem 352 helps you develop what you need to know to deal with that situation. Okay, so I'll just make the comment there that this is if thickness is not uniform. Okay. As far as closed thin-walled sections, let me kind of talk through that just a little bit. If you have a closed thin-walled cross-section, the way it tends to behave is that you have a shearing stress that kind of, roughly evenly distributes around the perimeter. If you have thicker sections in some places than others, that does play a part, and we're not going to deal with that case. So all of our, at least not in this class right now. So all of our things that we're going to do with closed thin-walled sections, we're going to use uniform thickness. But if you did have a difference in thickness, it would actually start changing how much shearing stress existed in the cross-section. But the idea here is that your shearing stress sort of evenly distributes around the perimeter of these closed thin-walled sections, and the actual shape doesn't matter very much. Like, we don't necessarily care if it's a square or a circle or a oval or an ellipse. It kind of behaves the same way, and we'll deal with some equations that help us get there. All right. That's about all the background material I wanted to talk about. Let's do a problem. Okay. I believe I did post this problem statement on Moodle. If I didn't, I can. It's not up? Okay, I will post it on Moodle. All right, so a torque of 50 foot-pounds. Let's say we're building a machine, and this machine needs to transmit this torque of 50 foot-pounds over a distance of 40 inches, maybe from one part of the machine to another part of the machine. And 3 different cross-sections are being considered for this task. Okay? The 3 cross-sections are all made of carbon steel. They all have 1-inch square outer dimensions, roughly speaking. Okay? One idea is that we could use a solid member that is 1 inch by 1 inch. Okay? Another idea is that we could use a closed square cross-section, and whenever you have this type of a cross-section, it is very common for the corners not to be perfectly squared. It's very common for them to have sort of rounded corners on them. And so this one has rounded corners such that the inner radius is 1/10 of an inch. Okay? And one little comment I'll make on that real quick is that if the corners are rounded, that is actually beneficial to the carrying of torsion in these members. If they have really, really sharp corners, that shearing flow that I talked about a minute ago doesn't happen quite as efficiently around those corners. So it helps a little bit to have these slightly rounded corners. All right, the wall thickness of this square member is 35 thousandths of an inch. Okay, and then our third option is basically the same exact cross-section as the closed member, but with an open section. So you see down here it basically has a slit in the cross-section. Okay, so this is also not uncommon to have a couple of options like this where, you know, it's likely that the option 2, in order to manufacture it, it may have needed to be welded at a particular spot in order to make that part. It doesn't always have to be that way, but that's a very common manufacturing technique to make a cross-section that is fully closed. Sometimes it has a seam that's welded. Okay, and so basically you can imagine this one just has a seam that's not welded. All right. And so what we're going to do is we are going to try to evaluate the suitability of each of these cross-sections for this task. And we're going to do that by evaluating how much maximum stress is induced in each of these cross-sections. Okay, that's step A. Step B, we are going to figure out what the angle of twist is for each of these types of cross-sections. And then lastly, we're going to figure out what the effective torsional spring rate is for each cross-section. So that's kind of how much torque it takes to turn or to twist it a certain amount of angle. The torque over the angle gives you your spring rate. All right?
Just curious, on the second one, the 1 inch, is that the outer?
Yes, so in each case, you know, and kind of my thinking whenever I stated this problem, let's say that this is going into a machine and the shape of the shaft is important because maybe it's involved in actually transmitting the torque, right? This is also not uncommon in machinery to have sometimes square-shaped shafts, because by having a square-shaped shaft you can put components on the shaft and the shaft will actually transmit those torques naturally due to the shape of the shaft and the shape of the corresponding hole in one of the components that you might put on the shaft. Okay? All right. So let's get going. What I'm planning on doing here is evaluating A, B, and C. I'll start with A and do all 3 cross sections. Then I'll go to B and do all 3 cross sections. C, all 3 cross sections. All right. Looking a little bit ahead before I actually start doing calculations on stress, for instance, one of the things that we are going to need to know, 2 of the things we're going to need to know. One of them is in equation 3, it actually appears in equation 345 and 346. There is this parameter that they use that is A sub m. Okay. And there's also another one that's labeled L sub m. Okay, and I figured it'd be worthwhile for me to define these and then do some work and figure out what they are, because they will be used for both cases 2 and 3 up here. All right, A sub m is the area enclosed by the median line of the tube's wall. Okay, so what that means is you basically look at, halfway across the cross section. If you take midway across there, that's the median line. And what we're doing with A sub m is figuring out how much area is bounded by that median line. Okay, and that's a parameter that we're going to need in both 2 and 3 up here, I believe. Okay, L sub m is the length of the median line. It's kind of the perimeter, right? It's how long is that median line. Okay, so there's going to be a little bit of geometry right here at the front of this problem. All right. And specifically for this case where we have the rounded corners. So what I'm going to do is make a little sketch of one of the corners. Okay, so imagine here's one of the corners and it is curved. Maybe something like this, and it has some thickness to the wall. Okay, and we'll look here at the median line. So I'm zooming way in on one corner of this part. All right. Now, let me also show this. If this corner wasn't rounded at all, it would do something like this, right? It would come down to here and come over to here, and actually the median line would also be different, right? What would the median line do? Kind of come down like this. This one would come over like this, right? And so it matters that these corners are rounded a little bit because that's going to change how much area is bounded by that median line. Okay? Well, let me do this. What if we were finding the area bounded by the line if these corners were, were super square like this one? All right. What would our equation be if we wanted to just handle the area enclosed? Okay, yeah. So we're going to do an area enclosed by a square cornered section first. And I think Marshall's suggestion there is that really what you're going to do is you're going to subtract half of the thickness on each end, right? To get this dimension to here, and then it would kind of mirror itself on the upper side. This is the thickness over 2. Do you agree with that? Okay. So if you subtract 1 full thickness, then that would give you a side of this square that's bounded by the median line. And so I would submit here that the area enclosed by a square-cornered cross-section would be 1 inch minus this 35 thousandths of an inch. Over 2, you wouldn't divide by 2, right? Because there's actually 2 of them. Okay, and that would be squared. Okay, well, how would I go from that to the area bounded by my actual median line? Well, here's how I think about it. I think about it by basically defining a square right here. Okay. Can I determine the dimensions of that square? Okay. I would say that I probably can because I know that the inner radius, this is one of the givens in the problem up here. You can see up here it says these radius values are 1/10 of an inch. Okay. That means that this right here is 1/10 of an inch. And if that's 1/10 of an inch, then what is this? Okay, it'll be 1/10 of an inch plus half of the thickness, right? Okay. And what I'm going for here is I would like to subtract off from my big area enclosed by the big square up there, I'd like to subtract off 4 of these. right? Because if I can do that, then I'm back to my area that I need. Okay, so how do I figure out the area of that? Okay, the area of the little square here, which is going to be 0.1 inch plus half of 0.035 inches, right, squared, right? But then I've got to subtract, you know, that's the full area. I've got to subtract the area of this quarter circle. Okay, so let's figure that out. So here I'll say the area of the yellow shaded shape. Okay, and what we're saying there is that the area of that is going to be equal to 0.1 inch plus 0.35 inches over 2 squared minus, what's the area of the quarter circle? Okay, yeah, pi, it will be divided by 4 because I only have a quarter of the circle. Okay, be careful there. I'm not dividing by 4 because it's the diameter form of the area. I need the radius, right? And I'm dividing by 4 because it's only a quarter circle. And then I take that radius value, which is 0.1 inch plus 0.035 inches over 2 squared. Okay. So what's the area that I have bounded by my, my median line? I can put these two together, right? I can say it's going to be 1 inch minus 0.035 inches squared minus 4 of these. Do you agree with that? Okay. So I'll subtract off 4 times. Tell you what, I'll do that in another row down here. 4 times this 0.1 inch plus 0.035 inches over 2 squared minus pi over 4 times 0.1 inch plus 0.035 inches over 2 squared. And this is A sub m. All right. And so once I plug all of that in, A sub m ends up being equal to 0.91937 square inches or so. All right, so dealt with a little bit of geometry there in order to figure out what that area enclosed by the median line would be. And I'll just make the comment, I believe I said it earlier, but I'll say it again. This is the median line, whether you're the area enclosed by the median line, whether you're talking about the closed cross-section or the open cross-section, because they have the same shape. It's just whether or not it's welded along that seam. All right. What about the length of the median line, L sub m? Okay. What we need to do there is, first thing we need to do is determine, so if we basically define a line right here and figure out what would the length be up to a similar line on the other corner, right? We have 4 little line segments that are that long. Okay, so we need to think about how far is it from here down to here. And subtract off 2 times that, subtract off of 1 inch 2 times that length. Okay? Well, that's just going to be 0.1 inches plus the full thickness, 0.035 inches. Okay? And so what that tells me is that, you know, this dimension up here is going to be 1 inch minus 2 times 1.035 inches. Okay, and I've got 4 of those. So that's what I'll start with for my L sub m. L sub m is going to be equal to 4 times 1 inch minus 2 times 1.035 inches. Pardon me? Yes. Appreciate that. Turns out decimal places matter. Yeah, thanks for catching that for me. All right, so we have 0.135 inches there, and we need to add, we have 4 of these little quarter circle arcs, right? Well, if you have 4 quarter circle arcs, it's really just the perimeter of the circle, right? Or the circumference, as we call it, the circumference of the circle. Okay, formula for circumference of a circle is 2 pi r, right? Where r is the radius to the median line. So I'm going to put here 2 pi times, I won't make the same mistake again, I'll do 0.1, right, inches plus half of 0.035 inches. And that is basically accounting for the entire circle because we have 4 different instances where we have these quarter arcs. Okay? All right, so we plug those values in, and L sub m ends up being 3.6583 inches. All right, so we've actually taken care of the most tedious part of the problem at this point. All right, now we just need to look at these values of stress and angular deflection and stuff. All right, so let's get a start on that. As I mentioned a second ago, we're going to start with step A, and we're going to do step A for solid and closed section and then open section. Okay, so we'll do step A, solid cross section. The formula for this, for maximum stress, is 340, so this is equation 340. Maximum stress is going to be equal to the torque divided by, here's a factor alpha that I'm going to have to talk about in just a second, alpha times B times C squared. Okay? And so we have to go in here and make sure we understand what each of these sides are. Okay? It says the maximum shearing stress in a rectangular B by C cross-section bar, it occurs in the middle of the longest side B. So B is your longest side. I'm only mentioning this and making a big deal about it so that I say it from the front. We have a square cross-section here, so it doesn't really matter to us. B is going to be equal to C, right? But if you end up with one where you have a rectangular cross-section that's, you know, different lengths of the sides, it's important that you don't mix those up. So B is the longer side. All right, what about this alpha? Okay, well, alpha is in this unnumbered table. I guess there should be two N's in there. Unnumbered table on page 116. Which isn't my favorite that table is unnumbered, but it gives you the ability to look up based on ratios of B to C. It allows you to look up factors alpha and beta. Beta is going to come up in one of our next steps, okay? But for now, we need alpha. And so for us, the ratio of B over C is just 1. And so alpha is going to be 0.208. All right? So our maximum stress then is going to be equal to 50 foot-pounds over 0.208 that I looked up out of that unnumbered table. And then I'll go ahead and express it this way. We have 1 inch times 1 inch squared. Okay. If we want to just plug this into a calculator, we need a conversion factor here probably, right? What do we need to do there? Okay, there's a foot right here, so we probably want to multiply this by 12 inches per foot. Okay, and so this allows us to find our maximum shearing stress, which is 2.885 KSI. All right. So that was for my square cross-section. Okay, for my closed, hollow cross-section that's shaped like a square with my rounded corners, the formula for that is equation 345. Equation 345 says that your maximum shearing stress is going to be equal to the torque applied divided by 2 times that area enclosed by the median line times the thickness of the cross section. Okay. So this gives me 50 foot-pounds over 2 times A sub m. We calculated down here. It was 0.91937 square inches. And then the last parameter there is the wall thickness. Okay, and the wall thickness is 35 thousandths of an inch. So my maximum shearing stress then in the closed hollow cross section with the rounded corners is going to be 9.323 KSI. Yeah, I have the answer down here. Probably is worthwhile mentioning that to get that number, we would want to put in at a conversion here of 12 inches per foot. All right, so there's our solid square It makes sense that our maximum stress would probably be a little bit larger if we don't have as much material helping to carry that torsional load, right? So that ends up being 9.323 KSI. And then for our last entry here, we're going to use equation 347. Okay. 347 is kind of an interesting equation because it's got two parts to it. Or there's actually two equations listed there. Okay, so the max stress that you get out of equation 347 is going to be equal to 3 times the torque divided by L C squared. Okay, and the L that we're talking about there is the length of the median line. So I'll go ahead and put that in there, that is L sub M. Okay, and keep in mind that this equation 347 is if you have uniform thicknesses of every segment of your open cross-section. Okay, one of your homework problems that I'm going to give you will have non-uniform thicknesses of the various segments. And so that's where I mentioned that exercise problem that you will probably want to check out. I believe it was 352. All right. So this maximum shear stress then is going to be equal to 3 times 50 foot-pounds over, let's see, it was down here, 3.6583 inches. Okay, multiplied by, and the C that they are talking about there, this is, annoying for a lot of students, but it doesn't necessarily maintain consistent meanings of your various letters that they use, the various variables that they use. So the C that they are discussing there is the thickness. It's that uniform thickness throughout that cross-section. The reason that they are using C is that this equation it comes out of the equation that we had over here for the rectangular cross-section. And C, remember, was the smaller of the lengths, right? So this C is actually consistent with this C over here, right? If you kind of think of where the roots of where that equation came from. All right, so we need to put in 0.035 inches, and then that is squared. Okay, again, we're going to need our conversion factor of 12 inches per foot, and when we plug all this stuff in, we get a maximum shearing stress of 401.66 KSI. That's a lot. Actually, what we would interpret that to mean, most likely, it's likely that our material would not have the strength to be able to carry that. And so, as soon as the material ceases to be elastic, then we basically wouldn't expect that any of our other conclusions that we might have might follow, right? So it's likely that this member would fail before it reaches that level of stress. All right? Interesting, huh? All right, so Next piece, we want to know what is the angle of twist for each of these. So part B, we'll start with the solid cross-section, and there's an equation on page 116, equation 341. Okay, equation 341 says that our angle of twist is going to be equal to TL over beta times B times C cubed times G, where G is the modulus of rigidity. All right, so we're going to plug in what we know for this scenario. We'll have 50 foot-pounds for our torque. The L that they reference there is the length of this member. Okay, so we might have to go back up here to remind ourselves that we had a 40-inch length. And I may as well go ahead and put in my 12 inches per foot at this time, because I do want to convert the foot in foot-pounds to inches. Okay. What about beta? Well, beta is looked up out of that same unnumbered table on page 116. We have a fraction of B over C equal to 1, and so we would look up a beta value of 0.141. Okay, B and C are both 1 inch. And G for carbon steel, you can get that out of table A4 in the back of the book, but it is 11.5 times 10 to the 6th psi. All right, and so theta then is going to be equal to, what units would this come out in, actually, before I answer that question? Yeah, the number that pops out of this equation ends up being unitless, right? And generally the way you will interpret that for these types of problems is that that means radians, right? So it turns out to be 0.015 radians, or 0.848 degrees. Okay, now let's look at our closed cross-section. Closed tube cross-section. All right, the equation for the closed tube is equation 346, which is on page 121. A good thing to note here is that this is actually noted as theta sub L. So equation 346, theta sub L. What they mean when they use theta sub L, this is actually an angle of twist per unit of length. Okay, so you got to be careful when you see that and don't interpret it as an overall angle of twist. As a matter of fact, if you're really careful with keeping up with all of your units, you would notice that it couldn't be just an angle of twist because it winds up with this extra length unit included in it. Okay, so theta sub L is just going to be equal to T times L sub M over 4G A sub M squared T. Okay, so we'll start plugging things in there. We have 50 foot-pounds. L sub M is, remember, the length of the median line, which was 3.6583 inches. And I'll put in my conversion factor from feet to inches up there as well. We'll take that and divide it by 4 times G. G is the same as it was in the last problem. 11.5 times 10 to the 6th PSI. All right. A sub M was this area enclosed by the median line, 0.91937. Okay, that would be inches squared. And then that value, that parameter, is squared. All right, and then lastly, we get this multiplied by the wall thickness. Say one more time. Yeah, this is our per length, and I tell you what, I'm going to go ahead and calculate this angle of twist per unit length, and I'll do that in a subsequent step. Okay, so it winds up being 0.00161 radians per inch. Or, oops, in degrees per inch, this is 0.092. Okay, if you want to know theta, you take one of these values, like 0.00161 radians per inch, and you multiply it by the total length of the rod. And that ends up giving you 0.065 radians. Or in degrees, this is 3.697 degrees. Okay, do those numbers seem to, at least, you know, relative in size to the last ones? Does that make sense? You think it would twist more? Yeah, it does. It does make sense. It would twist more because there's less material helping to carry the load because it's got the hollow middle. All right. Now, open cross section. This is where it gets a little bit interesting, because the equation is not stated perfectly in terms of theta sub L, right? What it does give us here is that G times theta sub L times C is equal to 3T over LC squared, okay? How I interpret that is that theta sub L, since we've already done, we've already calculated what our stress is, the shearing stress is, theta sub L can be basically be that maximum shearing stress divided by G times C. Okay, this is equation 347 again. Okay, so theta sub L is whatever we found for this stress down here, 401.66 KSI. Divided by 11.5 times 10 to the 6th PSI for G. And then C, again, is the thickness of the wall. All right. And if we plug these in, then we get an angle of twist per unit length of 0.998 radians per inch. What is that in degrees per inch? That is 57.176 degrees per inch. That's a lot of twist. Again, would it really do this? Oh. Yeah, we already sort of said that this thing is probably going to break before this happens. So again, with this one, we would take theta sub L and multiply it by the overall length. And so theta would be equal to 0.998 radians per inch multiplied by 40 inches. And this gives me a theta value of 39.917 radians, or 2,287 degrees. All right? So this is the point in the lecture where I say this. Open sections suck at torsion. Okay? This is, you know, if there's one big takeaway you take from today's lecture, it is do not use open sections to carry torsion if you can help it. Okay? Because it is a really bad way to carry a torsional stress and to have any sort of stiffness in a torsional orientation. All right? So, that's our big takeaway today. Open sections suck at torsion. Yes?
So, why doesn't the second and third we'll do thin wall the two thin wall
Yes.
Why don't they have the, they just went to the formula already? Because that's the first one does, so.
Yeah, I mean, I don't know the answer to that, why they wouldn't express them all the same way, but this is how we have them, and so, you know, to some degree, it can kind of be helpful sometimes to think in terms of angle of twist per unit length, because it's more of a function of just whatever the material in the cross-section is, whereas, you know, and it sort of eliminates one of the variables that would control how much twist you had overall. All right, so it kind of makes some sense to me that you might want to eliminate the L variable out of that, but, you know, we just take things as they come, right? Quick comment, talking about how open sections suck at carrying torsion. Have you ever taken a tube of paper and tried to twist it? Like, all you've done is you've just rolled up a piece of paper and you've tried to twist it. Does it twist pretty easy? Yeah, like really easy, right? Have you ever taken that same tube of paper and taped along the edge? Okay. If you do that sometimes and then try to twist it, you will find that it will support a lot more load in that torsional direction. Okay. That is the same exact principle as what we've dealt with right here. It's by closing that cross-section, you're making sure that the ends of that membrane are not allowed to move one relative to another down the length of the member that's carrying torsion. And by doing that, you greatly, greatly stiffen it and make it stronger. Okay, so these are some things to keep in mind whenever you're designing things for torsion and you're looking at the cross-section. Don't ever do it so that you leave it open if you can at all avoid it. All right, we have one last little piece that we need to do. What is it? Tell you what, I'm going to do it right here. Okay, spring rate. So the torsional spring rate, I'll do it right here, C. It is just going to be however much torque you applied over however much it twisted. Okay. So K is going to be equal to 50 foot-pounds over 0.015 radians. Okay. And we can express this in, we can actually leave the foot-pounds alone if we want. I mean, it's just up to us what kind of units we want to see. Because the units that will come out of this, you know, it's fine to just express it in terms of foot-pounds per radian, for instance. And for this one, it is 3,378.1 foot-pounds per radian. Or if we wanted to express it in terms of degrees, we would have 58.96 foot-pounds per degree. Okay. The K value here works the same way, 50 foot-pounds per 0.065 radians. And that comes out to be 774.98 foot-pounds per radian, which is 13.526 foot-pound per degree. All right, and then the last one here, K, is going to be equal to 50 foot-pounds over 39.917 radians, or that gives us 1.253 foot-pound per radian, or 0.02186 foot-pound per degree. All right, my last little comment I'll make here is, even though our open section sucks at torsion, and we don't really want to carry, if we can help it, we want to try to avoid carrying appreciable amounts of load in torsion in open sections. It will carry a little bit, right? So it's sometimes good to know that. And even though these values up here end up being ridiculous in that it wouldn't actually be able to twist by 2,287 degrees under this 50 foot-pound torque, what if we reduced that torque down to, you know, let's say 7 inch-pounds? A lot less, right, than 50 foot-pounds, or, you know, 1 inch-pound. Well, it might be able to support that, and if it did, then these K values are still valid, even though we developed them using these numbers that were ridiculous. Okay, so that's the point I wanted to make there, is that your torsional spring rates are still valid, even though we got them out of these numbers that seem kind of ridiculous. Actually, I have one more comment to make as well, and that is that I posted some homework that's based on this content. The 3 problems that you have on this homework coming up aren't all that difficult. You know, I think you'll be able to get them fairly easily. But if you look ahead into homework 17, there's another problem in there that involves the twisting of a truck frame. All right, that's a pretty hard problem, and I would actually recommend that y'all get started with that sooner rather than later. I put it in a later homework to give you plenty of time that you could look at it over several days, a couple of weekends worth. So anyway, do that, please, and I will see you guys when we meet next week. Have a great weekend.